Okay, let's kick things off. Welcome everybody, and thanks for joining this month's edition of the Dfinity Public Global R&D meeting. My name is David, and I'm your MC today. And as we can see here, we have an exciting agenda today. First off, we're gonna hear an update on SEV nodes on the IC by David. Then we are gonna hear about Canister Fuzzing by Venkatesh. And finally, we have two awesome demos. First off, the Dogecoin integration presented by Mathieu. And second, a demo about NNS recovery by Andrew and Pirugo. And with that, I directly hand over the screen to David, who is gonna talk about SEV nodes on the IC.
So, thank you very much, David. I would like to talk about the first SEV nodes. And SEV stands for AMD's Secure Encrypted Virtualization Technology, which provides a new level of enhanced confidentiality and integrity on the Internet computer. So this has been a feature that we've been working on for a long time. And now I'm happy to present all the new features that it's bringing. So let's look at the benefits of SEV. So first of all, it provides encrypted memory to the guest OS virtual machine. It also ensures that only verified versions of the guest OS is allowed to run. We can enhance the protection of data by ensuring that only the verified guest OSs have access to the data stored on the node. And it also allows us to remotely attest the version of the guest OS and the state of the virtual machine that a node is running. And I'm also happy to announce that the first SEV SMP nodes are live. So 4 unassigned nodes with SEV SMP have been live for several weeks. They have undergone multiple successful upgrades. And why this is important, I will let you know in a second. And now we also have proposals out to convert these nodes into API boundary nodes and replica nodes. Also, let me point out that on the dashboard, we have added a new field which shows whether a node is equipped with SEV. So you can see that by looking at this trusted execution environment active or inactive field on the dashboard. Now, I would like to explain all the new features in detail. And let's start with the RAM encryption. Here I'm showing how the ICOS looks like. We have the host OS, which is running on the bare metal. And inside the host OS, we run the guest OS in a virtual machine. The guest OS, all the important processes, such as the orchestrator, the replica, the Bitcoin integration, and also the canisters, they all run inside the guest OS, inside the guest OS virtual machine. And now, with SEV, we have added memory encryption, meaning that it's impossible for the host to see what's going on inside the virtual machine. Next, I would like to explain to you this concept, the SEV attestation report. This will make it easier for me to explain the rest of the features. So the SEV attestation report is a struct with fields such as the virtual machine measurement, the CPU ID, and some platform information, which encapsulates the state of the virtual machine. So first of all, the measurement. The measurement is a hash of the virtual machine. And this measurement expresses what code is running in the guest OS. So you can imagine if there is a change in the code of the guest OS, this measurement changes. The CPU ID identifies the CPU. This allows us to show what CPU is running on the node. And the structure is then signed by the AMD certificate chain, which ensures that when our software stack talks to the AMD secure processor on the node, which gives us the attestation report. There's no way for the host to intercept this call and return some kind of fake attestation report. Let's talk about disk encryption keys. So this shows how disk encryption keys are derived on SEV-enabled nodes. The whole process starts with the source code. We compile this source code and we get the guest OS image out of it. This contains multiple parts. So there is a root file system. That's the biggest output containing most of the binaries. But it, for example, also contains the init RAM disk, which contains binaries and code that runs during the early boot process. And some other things such as the kernel and a few other outputs. From the root file system, we calculate a root hash. And then the root hash, the init RAM disk, and a few other things are combined into the SEV measurement. The SEV measurement is calculated by the AMD secure processor when the virtual machine starts. From this SEV measurement, we derive, actually it's the AMD processor that derives an SEV sealing key. And then from this SEV sealing key, we derive a disk encryption key. And we use this disk encryption key to encrypt and decrypt the data partition. Meaning that if anything changes in the guest OS source code, the root file system or the init RAM disk or something will change in the guest OS image, meaning that the SEV measurement will be different, the SEV sealing key will be different, and of course, the disk encryption key will be different. So the data can no longer be decrypted. This ensures that only verified guest OS code has access to the data. Now the question arises how we can upgrade SEV-enabled nodes if whenever the guest OS changes, the data is not accessible anymore. And for this, we have developed a new upgrade process which ensures that only verified guest OSs have access to the data. I created this diagram to show this process in detail. So the whole upgrade process starts the same way as on non-SEV enabled nodes. Meaning that the old guest OS downloads the new guest OS upgrade image and writes it to the alternative partition on the machine. By writing to an alternative partition, we have a way to run the old guest OS and the new guest OS at the same time. After this is successful, the old guest OS requests the host OS to launch a virtual machine with the new guest OS. The new guest OS boots up and generates an SEV attestation report containing the measurement. Of course, this measurement is going to be different for the old and the new guest OS, since the new guest OS has a different code. At this point, the new guest OS talks to the old guest OS. It sends a request to the old guest OS over TLS and sends the SEV attestation report that it just generated to the old guest OS. The old guest OS checks the attestation report and compares the measurement with the base measurements that can be found in the NNS registry. The base measurements are calculated at compile time and is part of the proposal. So when the community accepts a proposal, they see exactly what measurements are accepted for this release. So the old guest OS compares the measurement, and of course it also verifies that the SEV attestation report of the new guest OS was signed by the AMD certificate chain, and this also verifies that the new guest OS is running on the same node as the old guest OS itself. And if all this verification is successful, the old guest OS then sends back the disk encryption key to the new guest OS. At this point, the new guest OS has access to the disk. It can decrypt the disk content, and the upgrade is almost finished. And the last new feature I want to mention is remote attestation. This allows other nodes to verify the state and the software that is running on one of their peers. How this works is very similar to the upgrade mechanism. So the verifier requests an attestation report from one of the nodes, and then as an answer, it returns this attestation report. And at that point, the verifier can verify different things about this node. Now, as I mentioned in the beginning, we already have a few nodes which are SEV enabled, and we are adding more and more nodes. But in the meantime, we are already working on new features. So currently, we are designing SEV recovery methods, which will allow us to do a recovery in an emergency case while still providing the guarantees for confidentiality and integrity that now we want to guarantee with SEV. And once we have a good way to recover SEV nodes, we will also start adding SEV subnets. These will be subnets which contain only SEV-enabled nodes. And in addition, they will also ensure that all the nodes that they talk to in the same subnet are verified upon connection. So while currently we have individual nodes that are SEV-enabled, in the future we want to make entire subnets SEV-enabled, which will be good because now if a node shares some data with another node, it's better if it can first ensure that the other node is also valid. So these are the two things that are still coming up. And I'm very excited that hopefully this will add a lot of new exciting guarantees for confidentiality and integrity. Thank you very much.
Very cool stuff. Thanks a lot for presenting this, and really nice to see more and more SEV nodes reaching the IC or becoming part of the IC. So really cool stuff. Thank you. And I guess next up is Venkatesh.
Hello, everyone. I'm Venkatesh. I'm from the product security team at Dfinity, and today I'm going to talk about canister fuzzing. Next slide, please. Yeah. What's canister fuzzing? It's a new Rust library which allows to build like coverage-guided fuzzes for canisters. It's language agnostic. Since it works on the WASM level, you can use it on any type of Rust protocol like TL, TypeScript, JavaScript canisters. And the library has already been published. I want you to go there and test it out. Now, why we need this library? There is currently a lack of automated tools for finding vulnerabilities in canisters. And existing tools like libfuzzer and AFL, these are fuzzing tools, only work on native binary, and they don't support WASM runtime, which ICP is based on. And how exactly are we going to achieve this? We plan to inject the canister WASM with branch coverage tracking code. We will use this libafl library to implement a fuzzing engine programmatically, and we will also use Pocket IC for IC emulation. I will see more details later. Next slide, please. Before going into canister fuzzing, let's talk about what's fuzzing. Fuzzing is the process of feeding programs, in this case, like a function execution with data that are modified using a feedback mechanism. The most common kind of feedback mechanism, which everyone knows, is maximizing code coverage. On executing each input, you inject some code, which gives you how much branches were taken in this code. And then when new inputs which discover new branches from previous run are marked as then interesting, and these are used in the node run. So you have this feedback mechanism of discovering new path, and this new path inputs which discover new path are used again, and then this feedback loops go on and on. And this is why fuzzing is powerful, because it's stateful. It depends upon feedback mechanism and improves its input, whereas something which most developers are familiar with, like prop test, is stateless. It just generates arbitrary bytes at test targeted, but between two runs, there is like no link. And some types of bugs that can be found with the fuzzing are memory, arithmetic, and logical. And why we stress fuzzing as like a good testing tool. Internally, we use fuzzing a lot for native code, and we have found like several high issues. And as you can see from the trophy case internally, so it's a battle tested way of like finding vulnerabilities. Next slide. Yeah. Now, canister fuzzing architecture. So the two main things which are changing are the instrumentation. So as I mentioned before, since the existing tools can't instrument WASM, we built a new library which does this instrumentation for us. When a method is executed, the branch coverage information is stored in a part of WASM memory, and we inject another WASM method which allows you to export this memory data from the WASM memory back into the fuzzing engine. And the existing fuzzing engines can't work on IC architecture, so you need some way of like building this library itself. So we use libafl, which provides you Rust bindings to build a fuzzing engine programmatically, and it can integrate with Pocket IC. And currently at this state, to build a new fuzzer, the developers only need to just implement a Rust try. Next slide, please. Yes. So how does the development flow look? I think most developers are familiar with an integration test with Pocket IC, where you generate the canisters WASM, install the canister WASM, you define the canister input which you need to call with, you define some invariance, you call the canister input with a method, and then verify the output and invariance. Here, invariants are some things which you can assert that it will never happen or will always happen in canister code, or it should happen. For example, you can see the example below where someone withdraws funds from your canister to the ledger for the user specified. Now you want to verify that the balance the person is withdrawing in the local balance is greater than what they're withdrawing. And once the withdrawing is done, the user gets the amount, and then the local balance is reduced. So these are the invariants which you check. Now in this new fastest thing, after you generate the canister WASM, you need to instrument the canister WASM. And instead of defining a single input, you define a set of inputs. These are called a corpus in fuzzing, where these inputs will be used as the starting case for generating new inputs. You define your next steps are defining invariants, calling canister method with the input, and then verifying output. Finally, the fuzzing engine takes all this coverage information, and then it mutates the bytes to generate new inputs. Then this goes on a loop, and you hope something catches with the invariance you defined. And as a side note, like writing good invariance is basically 80% of the work, and the rest of the thing is just the cherry on the top. Next slide, please. Yes. So now with the new library, all you need to do is implement this 3 steps or this 3 traits methods in this trait. And if you look at it, it's just clubbing these steps into the methods, and you're moving from your integration test to this method should be simple enough. One thing I want to mention is that we have this extra method called setup, which is useful for each run setup. For example, if a canister needs to have a particular balance for a local balance to make a test, you need to set this up every round. So it's also useful to have this extra method setup, which needs to be like a cleanup thing, which needs to be run every round. And with this, you just have a binary which works like a full-fledged fuzzer, and then you can test your canister indefinitely. Next slide, please. Now, with the development flow, I want to just jump a bit more technical into how the instrumentation works. The goal of the instrumentation itself is to capture the branch coverage along with how many times the branch was taken. These two are the things which is important for the fuzzing engine. So the step, if you see the example to the left, it's basically check whether a number is odd or even, and it has 2 branches, which is a if else branch, and it updates some value in the memory based on whether the value is even or not. Next slide, please. Yes. So the first step of the instrumentation is injecting some globals and system API imports. globals in WASM are the same as a global value in your code. The two globals which we inject are to track the previous branch and the starting index of the coverage map in WASM. I'll talk both about why these are needed later on. And we also need system API inputs. These are used to send the coverage map value from the WASM memory back to the fuzzing engine. You need IC system API to do this communication. Next step, please. Yes. Next, what we want to do is instrument the branches for coverage tracking. I think the methods are quite simple. At each branch, in this case, like a start of a function or if-else branch, after the branch is taken, we inject a constant value between in some range. And this value is generated at random during compile time to make sure each branch is uniquely represented. And then we call the instrumentation function with this branch identifier, which you'll see in the next slide. So what happens here? So as you can see, this local get 0. This is the value which we passed on for the branch identifier. I wouldn't go into too much details on this logic. As you can see, this is this battle-tested AFL tracking, which tracks how much branches were taken and in what pathway the branches were taken. This is a very compact way of storing the information. You might get some collisions between two values, but I think there is a good track record of the collisions being very small for like most of the code bases. And we want to use the same thing in our instrumentation as well. Next slide, please. And as I mentioned, we also need some way of like communicating the coverage from the host memory back into the user space. And in this method, we can see you append the data back with message reply data append and message reply. These are the system APIs, but we also want to clear the coverage map for the next run so that like when the new coverage is recorded in the next run, it doesn't mess up your readings. Next slide. Yes. One more thing is where to put the coverage map in WASM memory. Since WASM memory is linear, we want to make sure when Rust and Motoko code actually executes the programming logic, it doesn't interfere with where you're storing your coverage information. So we take some liberties and put this at the beginning of the WASM memory. So Rust and Motoko allocates the first 3 megabytes of the memory for the shadow stack, and this grows from 3 megabytes to 0. So we just need the 64 kilobytes of it. So it's kind of safe, but you still have some erroneous results if the code stack overflows. But I guess it's an acceptable trade-off unless you want to add like a new memory, for example. And next slide, please. Yes, and we want your feedback. As I mentioned, the library is already published. Please go to Canvas, start using it. And if you want to get started, there are examples in this Canister Fuzzing library. It shows like different ways of how we can implement this. And we look forward for your feedback on how we can improve this. Thank you very much.
Very cool stuff. I remember your fuzzers have always been very useful to locate tricky replica bugs. So it's very exciting that we can now also do fuzzing for canisters. So really great work. Thanks a lot. And with that, we already reached the demo section. And the first demo is going to be by Mathieu about Dogecoin integration.
All right. So hi, everyone. My name is Mathieu. I'm an engineer at Dfinity in the DeFi team. And I'd like to give you some updates about the Dogecoin integration that we announced a few months ago. And the good news is that the Dogecoin integration is now live on the IC. So it's open in beta, which means that it is feature complete, but we are still tweaking a few details here and there. But everyone can start using it. You can start using it from your canisters. And in this presentation, I'm actually going to show you how you can start using it. But maybe before that, some of you might wonder why Dogecoin, after having integrated Bitcoin, Ethereum, and Solana. And there are actually many reasons for that. The first reason is that Dogecoin is and has consistently been one of the top cryptocurrencies. So in terms of market cap, it has around 22 billions. So it's in the top 10. And if you look at the trading volume, so it also has massive volume traded daily. You have around, so these numbers were for today, around 2 billion of USD traded daily. Now, what's interesting is that if you look at the volume traded on centralized exchange and decentralized exchange, there is generally a gap for any currency. So for Bitcoin and Ethereum, this gap is around 2 orders of magnitude. But when you look at Dogecoin, it is 3 orders of magnitude. And actually, there hasn't really been any solid DeFi ecosystem for Dogecoin. And with this integration, we hope to change that. And we believe that it is the first safe way to actually build decentralized application that can use Doge. And so this can be a real enabler for DeFi for Dogecoin. And so we really see a strong potential here. So now let me show you in more details what this means for you developers. So we currently have a Dogecoin canister that is running on a system subnet. And this canister is able to directly communicate with the Dogecoin network. And it also exposes an API that your canisters can use to get the balance of any Dogecoin address, get their associated UTXOs, get the fees that are currently required for transaction on the Dogecoin network. You can also get the headers of the block, and you can also use that API to send transaction. So now, if you combine that with the existing threshold ECDSA API, you can generate keys and derive Dogecoin addresses from there, and you can also sign your transaction before sending them to the network. So you really have all the functionalities that are needed to build any kind of decentralized application that handle Doge natively. For instance, you can have Dogecoin smart contracts that can send Doge and that can also react to events that are happening on the Dogecoin blockchain. You can build decentralized exchange that run fully on-chain and that allows your users to trade Doge alongside with other currencies. And you can really build any kind of DApp that would use Doge as its native payment system, be it a social app, a gaming app, and so on. So yeah, we really hope to see lots of cool applications built on the IC that use Doge. And with that, it's time for a demo. So now what I'm going to show you, so before this presentation, I deploy a basic Dogecoin example canister that is able to interact with the Dogecoin canister. And I'm going to show you how you can use it. And after this presentation, you will be able to also deploy your own example canister and play around with it. So now we have 2 windows that you should be able to see. On the left-hand side, you have Dogecoin Block Explorer, which is for the Dogecoin mainnet. And on the right, you have the candid interface of the example canister that is able to interact with the Dogecoin canister. And so you have a number of endpoints. So we'll start by generating a pay-to-public key hash address, which is the standard address on Dogecoin. And what this does is that it will call the threshold ECDSA API to get a threshold public key and derive an address out of this public key. And so before this presentation, I actually top up this address with some Doge. So let's see how rich I am. And for this, I can call this get balance endpoint, which is going to call the Dogecoin canister to get me back the balance of that address. And here we can see a number. So unfortunately, this number is not the amount of USD I have, but the number of coinus, which is the smallest denomination you have in Doge. So it's the equivalent of Satoshi for Bitcoin. And so we can check if this matches what the Explorer gives me. And it seems like it's correct. So we have 17.8 Doge, which actually corresponds to 2.7 USD. And you can see here there is the history of the transaction. But now what I would like to show you is how I can send funds from that address to another Dogecoin address. So I'm going to use that endpoint for that and use this time a different address, which is this address, which is a real address on the Dogecoin network. And I am going to send 2 Doge or 200 million coinus. And what this does is a certain number of things, and this is why it will take a bit of time. So it will query the Dogecoin canister to know what are the current fees on the Dogecoin network. It will also fetch the UTXOs that are associated with my address to then use this UTXO to build my transaction, populate the output of the transaction with that address and this amount, sign the transaction by calling the threshold ECDSA API, and finally send the transaction to the Dogecoin network. And here we can see there is some updates that are available. And indeed, this transaction made it into the mempool of some Dogecoin miner. And so in a few minutes, we'll see this transaction being actually included into a block. But since it will take a few minutes, let's not wait. And I'll now go back to the slides. Okay, so as I was saying at the beginning of before showing you the demo, so these examples are available on the Dogecoin Canister repository. So you can see the code on how to interact with the Dogecoin API. You can also super conveniently deploy that basic Dogecoin example using ICP Ninja, where it will be available for 50 minutes. And so you can test the different endpoints that I didn't have time to show. And finally, if you have any questions, concern, or feedback, then feel free to discuss these on the forum. I just started the thread before this presentation, so you have the link here. And I have another announcement, which is that we are working on a new token called CK Doge. And as its name suggests, it's a token that is backed one-to-one with Doge, and that you will be able to use in the same way as CKBTC or CKETH to transact with Dogecoin on the IC. And yeah, that's it on my side. So thanks a lot to the Doge team for making this integration possible. And yeah, really looking forward to seeing all the cool applications that use Doge on the IC. Thank you. I'll stop sharing.
Thanks a lot. Very cool presentation. I guess I can't wait to build my first canister moving around Doge. And with that, I can only say much wow. And over to Pirugo and Andrew, who are going to talk about NNS recovery. I guess Pirugo is going to share right away. Yes. Awesome.
All right. Thank you very much, David. Hello, everyone. My name is Pirugo. I'm part of the consensus team here at Dfinity, and together with Andrew from the Node team, we'll speak about NNS recovery. So NNS recovery is a process that we designed Dfinity to recover from a catastrophic scenario where the NNS subnet would be stalled. So this could happen if, for example, there's a bug in the IC, which prevents nodes inside the NNS subnet from reaching consensus and basically stalling the subnet and preventing it from making any progress. So for that, we have a few requirements to recover from such a situation. We'd like to preserve the state as not to lose any data, minimize downtime, test it super thoroughly to not let any room for errors, and keep it as decentralized as possible to give Dfinity as less control as possible, and to, for example, letting everyone verify images. So a stalled NNS would be quite detrimental for the IC because, as you probably already know, the NNS is responsible for any upgrades of all the subnets in the IC, voting, rewards, ICP transactions. So all of these would be down if the subnet is down. In particular, also, the NNS is used to recover other subnets. So in traditional application subnet recoveries, we use the NNS to recover them. But here in that case, we can't use the same thing because the NNS itself is down. So instead, we'll have to ask help from our fellow node providers, from 2/3 of them. So that's a consensus quorum. So if 27 node providers cooperate out of the 40, we'll manage to revive the NNS subnet. And to do that, the node team developed a special UI in the host OS that we'll demo it later, and which allowed to download the recovery material from Dfinity's own object store, which is the same where we store IC upgrades, but we'll cover all of that in the next slides. So as a first step, I'll first present how we do traditional recovery, so for standard application subnets, because NNS recovery takes the same building blocks, but of course there are some technical challenges that will explain why they're different and how we can find alternatives. So in the recovery, we're in a situation where the guest OS version is broken, there's a bug, and we'd like to upgrade to a working one. And upgrades are made through cups. So CUP stands for catch-up package. It's a special message that peers exchange through consensus, and then that include the version of the guest OS that all the nodes should run. And normally, if everything goes well, this is created by the peers themselves by reaching consensus. But if that's broken, then we also the nodes also consistently monitor the NNS registry for a recovery cup. So anyone can do an NNS proposal to propose a recovery cup, which basically will tell the subnet to instead use that cup. And that is useful for recoveries because the nodes will see that cup in the registry and upgrade to the version that is inside of it, which hopefully fixes the bug. And so we need 2/3 of the node to do that, to then recover the subnet and reach consensus again. So one challenge, though, is that this cup also contains a state hash. So it contains a state hash to basically tell the nodes from what state to start again. And so the recovery coordinator, the one that creates this cup, needs to know to determine the latest state of the subnet as to not lose any state. And so they, in most cases in the past, it was Dfinity and Dfinity can check on the node that it has on the subnet, the state. But of course, we cannot rely on just that, because if it's lagging behind, then we would miss some heights. So what we do in advance is to do an NNS proposal to deploy an SSH key that grants read-only access to all the nodes inside the subnet, which allows to the recovery coordinator in Dfinity or elsewhere to read the state of the most up-to-date nodes and include that hash inside the recovery cup, and then do the second proposal. So that's for traditional recoveries for application subnets. And so for NNS recovery, we'll do most of the same thing, but of course we cannot do those two proposals because, well, the NNS is stalled. So for the one on the left, which is the second chronologically, to allow the nodes to have a recovery cup on their machine instead of fetching it from the registry, we will allow them to by a manual intervention from the node providers to upgrade to a special guest OS image. So Andrew will talk about that later on, but it will allow basically to download the cup from a known location, which is in practice Dfinity's object store. So if 2/3 of the nodes do that, then they will all agree on that version and go forward. And the proposal on the right, which is the first one that we actually do, we won't be able to actually deploy an SSH key on the subnet. And so instead, we use an SSH key that is already deployed today on the NNS subnet that grants backup access. And backup access is has fewer permissions than read-only. In particular, it cannot read the state, but it can read the consensus artifacts that all the nodes have. So the consensus artifacts are all the messages that all the nodes exchange with one another. And so you can simply replay them up until you reach the latest state. And so that's how we do it. So if the Dfinity own node is up to date, there's nothing to do. But otherwise, you can download the most up-to-date consensus artifacts and consensus artifacts from the most up-to-date node and replay it on top of that state to reach the latest state. Hash it, including in the cup, upload it to the object store, and then the node provider do the actions. So now I'll hand it over to Andrew, who will give us a bit more detail on how all of that fits together.
Guys, I'm Andrew. So yeah, we're going to talk about the NNS recovery process in a bit more detail, and yeah, what the recovery flow actually looks like. So I'm going to break down all these steps in detail, but just first at a high level, the NNS subnet goes down. The first step, the recovery coordinator prepares and hosts the recovery guest OS image and the recovery artifacts. The recovery coordinator, that's just a general term for whatever entity is orchestrating the recovery. In the near term, this would probably be a Dfinity engineer, but once the IC is fully matured, this can be any entity or individual in the IC community who's orchestrating the recovery. So yeah, they prepare the recovery guest OS image and the recovery artifacts. I'll talk about what exactly the recovery guest OS image is in a moment, and Carigo just talked about what the recovery artifact is and how that is acquired. That's primarily the catch-up packet. So then what happens? The recovery coordinator communicates to node providers the necessary recovery information, the recovery guest OS version hash, and the recovery artifact hash. We'll see this in action. And then the node providers complete the recovery process. And again, I'll talk in detail of what the actual recovery process is. And once 2/3 of nodes have successfully completed this recovery process, the NNS subnet is hopefully recovered. So you probably have a lot of questions, like one, what is the recovery guest OS image? It's the same as a regular guest OS image, except for a single recovery component, which downloads and applies these recovery artifacts so that all the nodes in the subnet can get on the same page for what reality is and resume consensus. And you also might be wondering, where are the downloads hosted? the same object store used for IC upgrades. Once the work has been done to repair and host these artifacts, the recovery coordinator would send out a message to node providers with all the necessary information. This would likely be a message in the matrix channel that we use to communicate with all the node providers, and then the node providers would complete the recovery process. And how will they initiate this recovery process? Well, we recently rolled out a limited host-OS console, which is just what it sounds like, a limited console for node providers to interact with their nodes directly. And you can see from the screenshot the available commands. They can see the system status. They can see the status of services. They can view logs. And one of the commands is initiating the manual recovery process, which brings up a user interface for the node providers to input these parameters. And we'll see this in action in the demo very shortly. But that still doesn't answer the question what the actual recovery process is. It's a 3-step process. The first one is for the host OS to download and upgrade the guest OS to the inputted recovery guest OS version. A quick reminder on what host OS and guest OS even is. David touched on this in his SEV presentation, but guest OS is where the core IC protocol exists, the replica, all the integration services with other blockchains. It's the core protocol of the IC. It's what people think of when they think of the IC protocol. And the host OS is the running environment for the guest OS. It's what launches the guest OS VM. But this is the partition layout. And you can see that each host OS and guest OS, they both have an AB partition layout, so that host OS and guest OS can each upgrade themselves. When host OS wants to upgrade itself, it writes the upgrade to its passive partition, and then it reboots into that partition, making the passive partition that partition. So that's how it upgrades itself. Why does this matter for recovery? In recovery, we are under the assumption that guest OS is completely broken, that it can't upgrade itself. So we had to implement a solution where host OS could upgrade the guest OS for it. So that's this step one. It's host OS downloading and upgrading guest OS to the inputted recovery guest OS version. And remember that recovery guest OS is the same as a regular guest OS. It just includes this special component, which you can see that that's basically step 3, downloads and applies the recovery artifacts after it comes up. And then once 2/3 of nodes have successfully applied these recovery artifacts, the subnet can resume consensus, or at least if all goes well. That's at a high level. The recovery coordinator prepares the recovery image and artifacts. It puts out the bad signal. The node providers all complete this manual recovery process, and once 2/3 of nodes have successfully done it, the subnet should resume consensus. So let's get into an actual demo and see it in action. I'm going to hand it over back to Pierugo, who's going to explain the current state of the testnet, and then I'll take over to act as the node provider to complete the recovery process. Sure.
Yep, thanks. So about 3 hours ago, I spawned up a testnet, which consists of an NNS of 4 nodes. And it's been 2 hours that it's broken, so it has a finalization rate of 0 blocks per second. And for the sake of time, I've prepared everything that needs to be prepared in advance. So I prepared the recovery guest OS image, the recovery artifacts that includes the cup. I uploaded it to the object store. I sent a message that you can see here on the screen to my fellow node provider, Andrew, containing the 3 values that he needs to perform the recovery. And I've myself did what he will present on 2 of the 4 nodes, which means 2 of the 2 nodes are recovered for now, and there's only 1 missing, which is Andrew's node, to reach the 2/3 threshold, which will be able to recover the subnet. So I'll hand it over back to you, Andrew.
Yeah. very quickly, we can see this finalization rate for the subnet. And yeah, it is completely stalled. So I'm a node provider. I see this message from Pierugo, or whoever the recovery coordinator is. And the first step is to identify the node and make sure I have console access. I have that right here. And it's being slow. There it is. So you can see this is the limited console I was talking about before, and I can interact with it. And this, I think, warrants its own demo in a separate R&D. So I won't get into it right now. But I can initiate the manual recovery process. Manual recovery. And this will perform a manual node recovery. Do not attempt this unless you are certain it is appropriate. I am certain. And this brings up the NNS recovery UI interface, where I can input the recovery parameters, the recovery guest-OS version, the hash of the recovery guest-OS, and the hash of the recovery artifacts. And I'll hit run recovery. I confirm these input values match yes. And the recovery will initiate. And we can see a lot of logs that the recovery process is going well, that the recovery guest-OS image is currently being downloaded and being written to the guest-OS so that the recovery guest-OS can come up. And this should take 15 seconds or so. And if all goes well, we should see a success message, which comes... There we go. Success, recovery completed successfully. So what does this success message actually indicate? It is just that first step. The hostOS downloaded and upgraded the guest-OS to the inputted recovery guest-OS version. hostOS then should launch the recovery guest-OS. That's why we see these boot up logs. If you're a node provider, you're very familiar with these boot up logs. And then it is currently undergoing step 3, where the recovery guest-OS downloads and applies the recovery artifacts. It should take like 30 seconds or so and give us a final success message. Manual recovery completed successfully. That is step 3. So now the node has the necessary catch-up packet, and all the nodes in the subnet should be on the same page for what reality is, and resume consensus. So if we go back to the Grafana dashboard, this should take just a few minutes, but we should see consensus resume very shortly. Until then, I will go through just a few more slides. So the big question is the subnet recovered? This is the question that all the Dfinity engineers will be frantically asking themselves and monitoring that dashboard to confirm. But while we're waiting for that, you might be wondering, why are we having to go through this manual process? Because it's not obvious. I think on first look, it doesn't seem like the most sophisticated process. And I'll just reiterate that there is no NNS to orchestrate the recovery of the NNS. That is what all traditional recoveries rely upon. And in an alternate design for NNS recovery, we could designate another trusted entity to orchestrate the NNS recovery, but this would give that entity control over the NNS, which we don't want to do. The NNS is like the root of trust for the IC. So this design, it still maintains a decentralized recovery process without undermining the NNS's authority and its security. And you might be wondering how it maintains a decentralized recovery process. And that's this last bullet point that I think is really important, that NS node providers, they're essentially voting to recover by going through this manual recovery process. Anyone can say, hey, we should do a recovery. I have these recovery artifacts. Everyone, all the NS node providers should go through this process. But the node providers should ask themselves, and we have guardrails in place, so they do ask themselves this: is the NNS down? Who is this recovery coordinator? Are they do they have any authority in the community? Are these recovery artifacts and the recovery guest OS image, is it publicly verifiable? And only then should they go through this process. And even then, we still require a critical number of node providers to go through this process to recover this, to recover the subnet. So it really is a decentralized recovery process, and without undermining the authority and security of the NNS. So I do think it's more sophisticated than it may look on initial glance. And if we go back here, we can see this is good news, right, Pierre-Hugo? Is that the confirmation one?
Yes, the authorization rate is back up, so
Fantastic.
is recovered.
We've recovered the NNS. It's great news.
That's
So, yeah, the status of NNS recovery, we're planning the first drill with real node providers in December, and then we should have periodic recovery drills every few months or so that node providers and us as engineers orchestrating the recovery process, we're all familiar with the process. And we'll hopefully never have to use any of this work, but until then, we're standing by. Big thank you to all the teams involved. This was a very much a cross-team effort to get over the finish line. And a big thank you to the node providers who are going to be the ones familiar with this process and who are going to do the work of completing recovery drills. And yeah, I see we're at time. So thank you, everyone.
Thanks a lot. Really awesome stuff. Great to see such a streamlined process for recovering the NNS if we ever have to. I agree that I also hope that we hopefully never have to actually, but still great to see that you guys have things under control. And with that, thanks everybody for joining this Global R&D today, and also thanks again to all the speakers for presenting.